Sometimes, the most pivotal and thrilling breakthroughs in astronomy don't originate from distant galaxies or the ancient edges of the universe, but emerge quietly in our Milky Way's neighboring regions, what we call the cosmic backyard. It is through such close-range observations that we often gain entirely new understandings and groundbreaking scientific perspectives on cosmic structures, gravitational interactions, and even the evolutionary journeys of galaxies. Recent data integration from multiple global observation teams suggests that the Large Magellanic Cloud LMC, a satellite galaxy located approximately 160,000 light-years from Earth, likely harbors a supermassive black hole of astonishing mass at its core. This discovery has sent shockwaves through the astronomical community. However, scientific progress often involves unexpected twists, and an unforeseen clue has steered this hypothesis in a radically different direction. Intriguingly, the support for this theory does not come from direct observations within the LMC itself, but from a series of seemingly unrelated yet extremely high-energy stars appearing in the Milky Way. These stars traverse the galactic disk at far normal speeds, moving like ejected interstellar bullets, leading scientists to speculate that they might originate from the epicenter of a powerful gravitational event. This unanticipated connection revealed by high-velocity stars from a neighboring galaxy challenges our traditional understanding of galactic structures, black hole formation, and stellar dynamic escape mechanisms, potentially even rewriting textbook theories. In this episode, we will follow the trajectories of these high-velocity stars to uncover their origins and driving forces step by step, and explore how these clues help scientists pinpoint the black hole hidden in the LMC's core, thereby deepening our understanding of galaxy interactions, dark matter distribution, and the operational principles of the cosmic gravitational network. The scientific journey begins with a group of celestial objects astronomers call hypervelocity stars, rare yet highly revealing cosmic phenomena. These stars are fundamentally different from our familiar Sun. While their masses vary, they share the common trait of possessing extremely high kinetic energy and speeds, far exceeding most stars in the Milky Way. Some hypervelocity stars travel at speeds exceeding 1,700 kilometers per second over 6 million kilometers per hour, fast enough to escape the Milky Way's gravitational pull and embark on interstellar journeys to infinity. In other words, these stars are no longer governed by the Milky Way's gravity. They are accelerating along trajectories that lead them out of the galaxy and into intergalactic space, like ejected cosmic voyages. Traditional wisdom holds that for a star to achieve such astonishing speeds, it must undergo extreme interactions with a supermassive black hole like Sagittarius asterisk at the Milky Way's core. Such interactions can release energy sufficient to accelerate stars to the galaxy's escape velocity. However, as more hypervelocity stars were discovered, their trajectories indicated they did not originate from the galactic core but from other regions, calling existing theories into question and forcing astronomers to rethink the dynamic relationship between black holes and stars. Enter the European Space Agency's Gaia mission, an unprecedented all-sky observation program dedicated to tracking the positions, distances, and velocities of over 1 billion stars in the Milky Way with millisecond precision, providing modern astronomy with an extraordinarily detailed galactic map. When scientists used Gaia data to perform three-dimensional dynamic analyses on 21 classified hypervelocity stars, they made a surprising discovery. These stars' movements were not randomly distributed but exhibited the directionality, suggesting their origins might not be singular. While the trajectories of several stars could be traced back to Sagittarius asterisk at the galactic center, at least 3 stars' velocity vectors pointed almost straight at the Large Magellanic Cloud, a precision alignment difficult to attribute to coincidence. Further statistical and dynamic analyses showed that 6 other stars' velocity vectors, metallicity, and spatial distributions were highly consistent with the LMC's gravitational environment and star-forming history, strengthening the likelihood of their origin from that galaxy. This result triggered a fundamental shift in thinking, forcing astronomers to reassess the LMC's gravitational potential and the scale of celestial objects it could host. The LMC is a relatively low-mass, loosely structured satellite galaxy with a total mass only about 1% of the Milky Way's. It was previously believed to lack the conditions to form supermassive black holes. Traditional theories posited that only massive spiral galaxies like the Milky Way, with high core density and matter accumulation, could nurture supermassive black holes, while galaxies like the LMC were thought to harbor only intermediate or stellar mass black holes. However, if the LMC can indeed eject stars at speeds exceeding its own gravitational escape velocity, a tremendously massive and energetic object must reside at its core, the strongest indicator of a black hole. What is the most plausible inference? Scientists are increasingly inclined to believe that the LMC's core likely hides a static black hole with a mass of hundreds of thousands of solar masses. This black hole dismantles binary star systems through powerful tidal forces and dynamic interactions, accelerating one star in the system to a velocity that allows it to escape the galaxy and ultimately enter our Milky Way. But how exactly can a galaxy eject stars at speeds exceeding its own gravitational binding energy? This brings us to a long-standing key question in stellar dynamics. The answer dates back to 1988, when astrophysicist Jack Hills proposed a theoretical model later called the Hills mechanism. It describes a high-energy celestial interaction capable of violently ejecting a star from a binary system. Specifically, when a pair of orbiting stars accidentally approaches a supermassive black hole, the black hole's powerful tidal gravity exerts violent stresses on the entire system, triggering an asymmetric energy exchange. In this cosmic gravitational tug-of-war, the black hole typically captures one star, pulling it into its orbit or consuming it, while the other is catapulted outward at extremely high speeds, becoming a hypervelocity escape star with speeds potentially reaching thousands of kilometers per second. Notably, this phenomenon is no longer just a theoretical hypothesis on paper, but an astronomical reality supported by concrete observational evidence. For example, the star S5HVS1, discovered in 2019 and traveling at over 6 million kilometers per hour, is strongly inferred to have been ejected after a gravitational interaction with Sagittarius asterisk at the Milky Way's core. This observation provided robust empirical support for the Hills mechanism. When applying the same dynamic model to the escape stars from the Large Magellanic Cloud LMC, the calculated mass of the potential black hole is approximately 600,000 solar masses, astounding for a dwarf galaxy. While smaller than the Milky Way's central black hole for million solar masses, this mass still represents an extraordinary proportional relationship to the LMC's total mass. Importantly, this estimate aligns with the mainstream model linking black hole mass to host galaxy mass, providing critical validation for its applicability in low-mass galaxies. Thus, the discovery of a less massive but dynamically potent black hole in a dwarf galaxy like the LMC is not only plausible, but also consistent with both observational data and theoretical frameworks, forming a coherent scientific narrative. Adding to the mystery, this hypothetical black hole reveals itself not through traditional visible signals, but indirectly via its gravitational influence on surrounding stars. Active black holes typically form accretion disks when consuming matter, emitting high-temperature radiation detectable in X-ray, visible light, or radio wavelengths. However, the LMC's putative black hole appears dormant, with little to no matter accretion, making it a true dark celestial object devoid of optical or high-energy emissions. It emits no X-rays, produces no high-speed plasma jets, and forms no bright accretion disk, rendering it invisible against the cosmic backdrop, an unseen leviathan detectable only by gravitational evidence. The only clues are the trajectories of hypervelocity stars, which act as ballistic evidence of the enormous invisible force that altered their fates. The potential existence of a supermassive black hole in the LMC not only revises our understanding of this galaxy, but also has far-reaching implications for galaxy formation theories, black hole evolution models, and cosmic structure distribution. Mainstream theories long assumed supermassive black holes resided exclusively in massive, complex galaxies like the Milky Way or Andromeda as end products of galaxy evolution. If a system as small as the LMC 1% the mass of the Milky Way can host such a black hole, current surveys may drastically underestimate the universe's supermassive black hole population, possibly by factors of tens or hundreds. This discovery has also spurred new dynamic surveys of other nearby dwarf galaxies, for example, Phoenix or Sagittarius dwarf, to search for similar hypervelocity star signatures and verify whether such systems commonly harbor underestimated black hole cores. Once regarded as rare cosmic anomalies, hypervelocity stars are now emerging as high-value astronomical tools, opening unprecedented observational frontiers. Like cosmic messengers crossing galactic boundaries, they carry physical signatures of their birthplaces and record gravitational interactions along their journeys, providing astronomers with otherwise unobservable data for gravitational topographies. By combining these stars' spatial velocities, orbital backtracking, and spectral metal abundances, scientists can indirectly reconstruct their origins, trace hidden black holes, map dark matter distributions, and even unravel ancient galaxy interaction histories. These insights extend beyond local observations, gradually reshaping our holistic view of how galaxies interact, merge, and influence each other's evolutionary trajectories. Far from being a passive satellite, the LMC is engaged in complex gravitational grappling and matter exchange with the Milky Way, acting as an active participant in galactic construction, even a key source of stellar material for the Milky Way. Hypervelocity stars ejected by the LMC eventually disperse into the Milky Way's outer halo, becoming part of this tenuous but critical stellar population. This raises intriguing questions. Does the Milky Way itself exert similar effects on its satellites? Can its black hole eject stars into other galaxies or intergalactic space? Might these stars seed new planetary systems in distant galaxies or disrupt stellar environments as interlopers? Such inquiries are opening new chapters in galactic archaeology and galaxy evolution research, a field dedicated to reconstructing billions of years of cosmic history from stellar motions and distributions. Excitingly, these discoveries also intersect with the rapidly advancing field of gravitational wave astronomy, offering deeper observational windows into the universe. If the LMC's black hole formed through early galaxy mergers or massive celestial interactions, these processes likely emitted faint but enduring gravitational waves. Current ground-based detectors like LIGO and Virgo cannot yet capture such long wavelength signals, but the upcoming Laser Interferometer Space Antenna LISA, scheduled for launch in the 2030s, may finally detect these cosmic echoes. This cross-disciplinary approach, multi-messenger astronomy, combines optical observations, stellar dynamics, and gravitational wave signals to piece together cosmic events from multiple perspectives, akin to using multiple sensors to reconstruct a distant cosmic symphony. At the heart of these revelations lies the Gaia mission's extraordinary contribution. This ESA initiative is reshaping our view of the Milky Way and its neighbors with unparalleled astrometric precision, reaching microseconds, equivalent to spotting a coin on the moon, allowing astronomers to measure star-level gravitational wobbles caused by nearby massive objects like black holes or dark matter clumps. This technological and theoretical breakthrough proves that even without traditional X-ray or electromagnetic observations, meticulous analysis of stellar motions can see otherwise invisible massive celestial bodies, like detectives reading cosmic tea leaves. Astronomers now infer the presence and scale of dark forces through subtle stellar clues, lifting the veil on the universe's most elusive structures. Thank you for joining us on this awe-inspiring journey through black holes and hypervelocity stars. If this content has sparked your curiosity about the cosmos, please like, subscribe, and enable notifications to stay updated on the latest astronomical discoveries and cosmic explorations. In our future interstellar adventures, let us keep gazing upward, for every look at the sky brings us closer to unraveling the universe's deepest truths.